In mathematics, a Kleinian group is a discrete subgroup of PSL. The group PSL of 2 by 2 complex matrices of determinant 1 modulo its center has several natural representations as conformal transformations of the Riemann sphere, and as orientation-preserving isometries a three-dimensional hyperbolic space H3, and as orientation-preserving conformal maps of the open unit ball B3 in R3 to itself. Therefore a Kleinian group can be regarded as a discrete subgroup acting on one of these spaces. There are some variations of the definition of a Kleinian group. Sometimes Kleinian groups are allowed to be subgroups of PSL2 extended by complex conjugations. In other words, to have orientation-reversing elements, and sometimes they are assumed to be finitely generated, and sometimes they are required to act properly discontinuously on a non-empty open subset of the Riemann sphere. A Kleinian group is said to be of type 1 if the limit set is the whole Riemann sphere, and of type 2 otherwise. The theory of general Kleinian groups was founded by Felix Klein and Henri Poincaré, who named them after Felix Klein. The special case of Schottky groups had been studied a few years earlier, in 1877, by Schottky. Definitions. By considering the ball's boundary, a Kleinian group can also be defined as a subgroup gamma of PGL, the complex projective linear group, which acts by Mobius transformations on the Riemann sphere. Classically, a Kleinian group was required to act properly discontinuously on a non-empty open subset of the Riemann sphere, but modern usage allows any discrete subgroup. When gamma is isomorphic to the fundamental group of a hyperbolic 3-manifold, then the quotient space H3, gamma becomes a Kleinian model of the manifold. Many authors use the terms Kleinian model and Kleinian group interchangeably, letting the one stand for the other. Discreteness implies points in B3 have finite stabilizers, and discrete orbits under the group G. But the orbit GP of a point P will typically accumulate on the boundary of the closed ball. The boundary of the closed ball is called the sphere at infinity, and is denoted. The set of accumulation points a GP in is called the limit set of G, and usually denoted. The complement is called the domain of discontinuity or the ordinary set or the regular set. Alpha's finiteness theorem implies that if the group is finitely generated then is a Riemann surface orbifold of finite type. The unit ball B3 with its conformal structure is the Poincaré model of hyperbolic 3 space. When we think of it metrically, with metric it is a model of three-dimensional hyperbolic space H3. The set of conformal self-maps of B3 becomes the set of isometries of H3 under this identification. Such maps restrict to conformal self-maps of which are Mobius transformations. There are isomorphisms, the subgroups of these groups consisting of orientation-preserving transformations are all isomorphic to the projective matrix group PSL via the usual identification of the unit sphere with the complex projective line P1. Finiteness conditions. A Kleinian group is said to be of finite type if its region of discontinuity has a finite number of orbits of components under the group action, and the quotient of each component by its stabilizer is a compact Riemann surface with finitely many points removed, and the covering is ramified at finitely many points. A Kleinian group is called finitely generated if it has a finite number of generators. The Alpha's finiteness theorem says that such a group is of finite type. A Kleinian group gamma has finite covolume if H3 gamma has finite volume. Any Kleinian group of finite covolume is finitely generated. A Kleinian group is called geometrically finite if it has a fundamental polyhedron with finitely many sides. Alpha showed that if the limit set is not the whole Riemann sphere then it has measure 0. A Kleinian group gamma is called arithmetic if it is commensurable with the group norm 1 elements of an order of quaternion algebra A ramified at all real places over a number field K with exactly one complex place. Arithmetic Kleinian groups have finite covolume. A Kleinian group gamma is called cocompact if H3 gamma is compact, or equivalently SL gamma is compact. Cocompact Kleinian groups have finite covolume. A Kleinian group is called topologically tame if it is finitely generated and its hyperbolic manifold is homeomorphic to the interior of a compact manifold with boundary. A Kleinian group is called geometrically tame if its ends are either geometrically finite or simply degenerate. Examples: Bianchi groups. A Bianchi group is a Kleinian group of the form PSL, where D is a positive square-free integer. Elementary and reducible Kleinian groups. A Kleinian group is called elementary if its limit set is finite, in which case the limit set has 0, 1, or 2 points. Examples of elementary Kleinian groups include finite Kleinian groups and infinite cyclic Kleinian groups. A Kleinian group is called reducible if all elements have a common fixed point on the Riemann sphere. Reducible Kleinian groups are elementary, but some elementary finite Kleinian groups are not reducible. Fusion groups. Any fusion group is a Kleinian group, and conversely any Kleinian group preserving the real line is a fusion group. More generally, any Kleinian group preserving a circle or straight line in the Riemann sphere is conjugate to a fusion group. Koba groups. A factor of a Kleinian group G is a subgroup H maximal subject to the following properties. H has a simply connected invariant component D. A conjugate of an element H of H by a conformal bijection is parabolic or elliptic if and only if H is any parabolic element of G fixing a boundary point of D is in H. A Kleinian group is called a Koba group if all its factors are elementary or fusion. Quasi-fusion groups. A Kleinian group that preserves a Jordan curve is called a quasi-fusion group. When the Jordan curve is a circle or a straight line, these are just conjugate to fusion groups under conformal transformations. Finitely generated quasi-fusion groups are conjugate to fusion groups under quasi-conformal transformations. The limit set is contained in the invariant Jordan curve, and it is equal to the Jordan curve. The group is said to be of type 1, and otherwise it is said to be of type 2. Schottky groups. Let Ci be the boundary circles of a finite collection of disjoint closed disks. The group generated by inversion in each circle has limit set a Cantor set, and the quotient H3, G is a mirror orbifold with underlying space a ball. It is double covered by a Handel body. The corresponding index 2 subgroup is a Kleinian group, called a Schottky group. Crystallographic groups. Let T be a periodic tessellation of hyperbolic 3 space. The group of symmetries of the tessellation is a Kleinian group. Fundamental groups of hyperbolic 3 manifolds. The fundamental group of any oriented hyperbolic 3 manifold is a Kleinian group. There are many examples of these, such as the complement of a figure 8 knot or the Seifert-Weber space. Conversely, if a Kleinian group has no non-trivial torsion elements, then it is the fundamental group of a hyperbolic 3 manifold. Degenerate Kleinian groups. A Kleinian group is called degenerate if it is not elementary and its limit set is simply connected. Such groups can be constructed by taking a suitable limit of quasi-fusion groups such that one of the two components of the regular points contracts down to the empty set. These groups are called singly degenerate. If both components of the regular set contract down to the empty set, then the limit set becomes a space-filling curve and the group is called doubly degenerate. The existence of degenerate Kleinian groups was first shown indirectly by Bors, and the first explicit example was found by Jurgensen. Cannon and Thurston gave examples of doubly degenerate groups and space-filling curves associated to pseudo-Anisov maps.